3:47 a.m., deep inside Russian territory. Something unthinkable is happening, for Ukrainian drones are flying directly toward Moscow at 380 kilometers per hour, completely invisible to Russia's dense air defense network. On the S-400 radar screen near Ryazan, the operator sees a faint cluster of signals. It looks like a flock of birds. But birds don't fly in perfect formation, and they definitely don't head straight toward Russia's largest oil refinery. When the drones are just 52 kilometers from the target and only 27 kilometers from the S-400 launch site, the lead drone suddenly climbs to 800 meters altitude. A surface-to-air missile would take 27 seconds to intercept at that range. The drones need only 41 seconds to reach the radar's blind zone. That gives the commander just 14 seconds to make a decision. Is this a real threat or just a decoy? In those few seconds, he must weigh everything. Each missile costs $2 million, 10 seconds left. The approach speed looks very real, 7 seconds. Rules of engagement require target verification, 5 seconds. If it's real, you have to shoot. 248 and 6 DM missiles launch, shrieking out of their tubes, accelerating to Mach 6 in just 3 seconds. But then, the drones suddenly dive to 200 meters, disappearing from radar. And here lies the S-400's fatal flaw. Its missiles have no onboard radar. They rely entirely on ground-based illumination radar to track the target. Once the radar loses the signal, the missile is completely blind. The commander stares at the screen. The target has vanished. The missiles keep flying on last known coordinates, then explode at 80 meters altitude, where the drone used to be. 180 kilograms of explosives shred the air into 24,000 steel fragments, but they only tear apart empty sky. The drones, unharmed, keep racing toward Moscow. 3:52. The two remaining Panzer S-1 units have only 17 seconds left to detect and respond. Their 1RS-2-1E radar, operating in the UHF/EHF band, is optimized for larger targets. So against drones with a radar cross-section, RCS, of just 0.1 square meters at a range of 8 kilometers, the signal barely rises above background noise. 12 seconds left, the operators see a flickering trace on screen. 8 seconds, the signal blinks, then disappears. They try to rotate the twin A-38M autocans, but the hydraulic system needs 3.2 seconds to rotate 180 degrees. There's almost no time left. At that moment, the lead Beaver drone locks onto its target and strikes at 3 hours 52 minutes and 17 seconds. The 3 other Beavers follow, each one hitting its mark in sequence. The immediate result, 140,000 tons of fuel ignited. Within 90 seconds, the western section of the refinery turned into a sea of fire, temperatures surging to 1,200 degrees Celsius. The blaze is expected to burn for 72 hours, and 40% of Moscow's fuel supply is now cut off. And this is just the beginning. 470 kilometers away, Novokivishsk, for 03 a.m. Russian air defense units believe they are ready. 3 Panzer batteries are deployed in a triangle formation. Their 1RS-2-1E radars can track up to 20 targets and engage for simultaneously within a 20 kilometers range. Commanders are confident this time the Ukrainian drones won't get through. But then something strange happens. Out of 12 drones, suddenly climb to 1,500 meters, fully exposed on radar. Instantly, the automated system reclassifies the targets. The radar returns from these drones match those of KH-101 cruise missiles, same speed, same radar signature, same signal strength. In reality, it's a deception. The high-flying drones have released corner reflectors, small triangular aluminum pieces designed to amplify radar returns. A reflector just 10 centimeters wide can appear on radar like a 10 square meters object. As a result, the Panzer radars believe they're facing real missiles. The battery commander has just 2 seconds to decide. And per rules of engagement, cruise missiles are top priority threats. Everything else must be put on hold. With the system now in full response mode, 857 times 10 to the power of 6 missiles are launched within 12 seconds, each accelerating to around 1,300 meters per second. For the first 18 kilometers, the missiles follow command guidance, then switch to semi-active homing. Then something strange appears on the radar screen. The targets begin making abrupt maneuvers, as if pulling 9G turns, a behavior impossible for real KH with 101 missiles, which can only withstand about 3G. The real reason is simple. Each drone has been dropping corner reflectors, small triangular bits of aluminum. When radar waves hit them, the signal bounces straight back, magnified, making a small piece look huge on radar. The drones release these reflectors every 2 seconds rhythmically. As a result, new targets constantly appear, while older ones fall away. On the radar screen, the number of targets multiplies rapidly, 8, 16, 32. The bitter consequence: millions of dollars worth of missiles are launched to chase cheap aluminum scraps, while the real strike force, the other drones, slips in from behind the command post, unopposed. While everyone's eyes were fixed on targets at 1,500 meters, 8 UJ-22 drones approached from the opposite direction, flying at just 50 meters altitude. This exploited a fatal weakness in the Panzer system. Its fixed phased array radar only scans a plus or minus 45 degrees arc. To look behind, the entire 3,000 kilograms turret must physically rotate, a process that takes 4.7 seconds. The commander shouted, "Rotate the turret, now." But it was too late. The drones were already within 1.2 kilometers. Each 57 times 10 to the power of 6 missile requires 1.5 seconds to arm after launch. At that range, they would collide before the warhead could activate. 2 twin A-38M autocannons deployed and opened fire with a deafening roar. Each barrel had an extremely high rate of fire, while the fire control computer calculated a leading angle based on the drone's lateral velocity, approximately 200 kilometers per hour, meaning the system had to fire 31 meters ahead of each drone's actual position. But the UJ-22 was built precisely to counter such a situation. Every 2 seconds, it would randomly change altitude between 40 and 80 meters, guided by barometric pressure sensors. The fire control system predicted each drone's position 0.8 seconds in advance, but with continuous altitude shifts, all predictions became flawed. Hit probability dropped from 83% to just 31%. The result: one drone was struck, disintegrating 300 meters from the target, but the other 7 got through, and 3 of them scored direct hits. Moments later, the third wave of attacks began. All 3 Panzer batteries started to reload simultaneously. Automated systems retracted the spent launch tubes, drew fresh missiles from storage under the turret, and mounted them onto the launch rails, preparing for the next round of defense. But the reload process takes 90 seconds. 90 seconds of total vulnerability. In that brief window, the refinery took 3 more direct hits. The Ukrainian planners had calculated it all down to the second. They knew exactly when the enemy would be defenseless. But at the next target, the Russians had quietly deployed an ace up their sleeve, one the Ukrainians hadn't yet detected. At 4:18, 6 UJ-26 Beaver drones approached Voronezh, and then suddenly lost navigation. GPS vanished. Comms went dead. Navigation screens showed nothing but white noise. The reason: a Krasuka for electronic warfare vehicle had just activated. But this wasn't ordinary jamming. It flooded the entire electromagnetic spectrum from 0.1 to 18 gigahertz, with directional power output of 500 watts. To understand the scale, a real GPS signal has a strength of only 0.025 watts, broadcast from satellites 20,000 kilometers above Earth. Krasuka overpowered that signal by a factor of approximately 5 quadrillion. It's like trying to hear a whisper while standing next to a screaming jet engine. Cut off from GPS, the drones switched to inertial navigation, relying on their gyroscopes. But these gyros drift by about 10 degrees per hour. After 68 minutes of flight covering 380 kilometers, accumulated error could push them 200 meters off course, and that kind of deviation could doom the entire mission. At this point, the drones entered a state of systemic crisis. Temperatures inside the fuselage rose to 95 degrees Celsius, triggering thermal throttling. The processor slowed down to avoid permanent damage. Slower processing meant fewer visual comparisons per second. The system began cutting non-essential processes to survive. Navigation lights, off, saves 2 watts. Data transmission, off, saves 5 watts. Radar warning receiver, off, saves 3 watts. Each watt saved dropped the temperature by 0.5 degrees C, equal to a gain of 100 megahertz in processing speed. 30 seconds to target, the algorithm still hadn't matched a visual pattern. 20 seconds, internal temperature hits 98 degrees Celsius. 10 seconds, the system was nearing thermal shutdown. 8 seconds, finally a pattern match. But not a pattern from the tanks themselves. Those were obscured by smoke and harsh lighting. Instead, the AI recognized the geometric relationship between three shadows. Three distinct shadows forming a triangle, with fixed angles, a signature that doesn't change with lighting. Using this, the location of Tank 7 was pinned with a margin of error of only 4 meters. But that data existed only in the memory of one drone, and communications were completely jammed by the Krasuka system. Unless the lead Beaver drone took a gamble. It activated frequency hopping, broadcasting across 1,000 frequencies per second, based on a pseudo-random pattern nearly impossible to predict. This made it extremely difficult for Krasuka to lock on, opening a brief transmission window, just long enough to send the most crucial information. Krasuka couldn't jam all frequencies at once with equal power. At channel 847, for just a microsecond, a gap appeared. The drone seized the opportunity, transmitting just 128 bytes, GPS coordinates, and impact timing. 5 other drones received the burst, verified the data, and adjusted their flight paths accordingly. 420. The warhead struck right where steel met concrete, an engineered weak spot caused by thermal expansion mismatch, igniting the fuel reservoir. The Krasuka, for crew abandoned ship, leaving behind a multi-million-dollar electronic warfare vehicle. As the jamming signals faded, 8 more drones reappeared on radar, heading straight for one of Russia's most heavily defended military targets. At 4:32, the Primorsk-Akhtarsk airbase, thought to be impenetrable, faced its test. It had 4 Tor M2 systems positioned in a diamond formation, each spaced 5 kilometers apart, creating overlapping coverage zones. 2 Su-35 fighters patrolled at 8,000 meters, and every radar was fully operational. Commanders were confident the 8 UJ-22 drones wouldn't make it through. But Ukraine had discovered a detail Russia overlooked. Observers noticed the UJ-22s didn't fly in straight lines. Instead, they followed a snake pattern, technically a sine wave flight path. This added about 8% to the total distance, burning an extra for 0.3 liters of fuel per drone, a price deemed acceptable for the tactical edge it provided. Why the erratic path? Because Tor M2 and its fire control systems rely on command guidance and trajectory prediction. Each time a drone curved unpredictably, the system had to recalculate. It used a Kalman filter to forecast motion. But that filter assumes relatively stable behavior. The random oscillations introduced what's called process noise, causing prediction errors to accumulate. By the time a missile was launched, it could be up to 50 meters off target, enough to compromise interception. Then came the salvo. All 4 Tor M2s fired simultaneously. 16 9M338 missiles screamed into the sky, accelerating to Mach 2.5. Their guidance unfolded in 3 stages. Inertial navigation for the first few seconds. Command guidance until they closed to 2 km. Then active radar homing for the terminal phase. This created a kinetic kill volume, a moving box of death from which no target could escape. 10 seconds to impact. Closing speed, 850 m/s. 9 seconds. 8 seconds. The missile seekers locked on, then something unexpected happened. The UJ-22s suddenly pitched upward, pulling 6 G climbs, shooting from 180 meters to 1,200 meters in just 4 seconds. The 9 minutes and 338 seconds tried to follow, but couldn't keep up. These missiles used aerodynamic control via small canards, which stalled at steep climb angles, is almost equal to 76 degrees. The airflow separated from the surface, nullifying control authority. Their thrust vectoring had only plus or minus 12 degrees range, too limited for that kind of vertical maneuvering. Most missiles shot harmlessly below the drones. Only one missile detonated. Its proximity fuse locked onto the infrared signature above, 400 degrees C exhaust, triggered the warhead, and released 3,500 tungsten fragments in a focused cone, obliterating that drone. But that dramatic interception? It was just a diversion. While every radar and weapon pointed skyward, no one noticed the real threat from the sea. Just 15 seconds later, 4 UJ-26 Beaver drones banked toward the coast. They had flown 700 kilometers across the Sea of Azov at only 5 meters altitude, using radar altimeters to HUD the wave tops, requiring constant adjustments due to the sea's reflectivity differences versus land. At 5 meters altitude, the radar horizon is only 8 km, meaning coastal radars couldn't see them coming until it was far too late. The result, the Shahed storage hangars were completely exposed. In Hangar 2 alone were 30 Shahed, 136 drones on maintenance racks, each carrying 40 kg of explosives, C4/RDX, and 50 liters of fuel. That's 200 kg of explosives and 1,500 liters of fuel packed into a 40M superscript 2 area. An explosive density of 30 G/M superscript 2, 10 times the NATO safety standard for ammo depots. The first Beaver slammed into the roof of Hangar 2. The roof flipped open as the drone's wreckage flew 50 meters into the air before crashing down. 1.3 seconds later, Hangar 3 exploded, followed by Hangar 4. Within 45 seconds, over 200 Shahed drones, estimated at $6 million USD, were destroyed. At 3:47, an emergency scramble order was issued, but the runway was blanketed in thick smoke. Visibility had dropped to just 150 meters, while the minimum required for a Su-35 to take off is 200 meters. The result, the Shahed production base at Moscow, Okhtarsk, was effectively rendered inoperable. By theory, this should have been impossible. The standard range of a Beaver drone is only 350 km. But 2 of them had been modified. Engineers sacrificed 5 kilograms of explosives from 15 kilograms to fit an auxiliary fuel tank in the front bay, adding 12 liters of extra fuel. The result, a total range of 980 km with 30 minutes of fuel reserve. A Su-35 fighter patrolling the area tracked them for over 20 minutes. The pilot switched his Urbis-E radar to narrow beam mode 10 degrees at maximum power, focusing energy to achieve maximum detection range. With a small radar cross-section, 0.1 M superscript 2, the Beaver was solidly tracked, and its path was now exposed. The drone had no way to evade, no flares, no jammers, no countermeasures. The pilot launched 2 R-77 missiles from 18 km out, then immediately banked away. The R-77 uses an active radar seeker, Argus 9B2. Once launched, it operates autonomously. The missile accelerated to Mach 4, covering 18 kilometers in 13.2 seconds. At 12 km, the seeker activated, capable of tracking targets maneuvering up to 12 G. The Beaver could manage only 6 G. But the drones pulled off a clever trick. They simultaneously rolled on their axis while quickly shifting altitude between 150 meters, producing an angular velocity of 150 degrees/second, faster than the seeker's gimbal could physically rotate. The R-77's guidance updates 100 times per second, but its mechanical seeker couldn't rotate fast enough to keep lock. It suffered a classic gimbal lock failure. The result, the first R-77 triggered its proximity fuse at 80 meters, spraying hundreds of 8mm tungsten pellets. Ripping through the drone's frame, the Beaver was destroyed. The second missile scored a direct hit, turning the second Beaver into shrapnel and aluminum confetti. One drone was heavily damaged, but its flight computer recalculated a final trajectory. After 40 seconds of wobbling, it adjusted its course, boosted thrust in the final minute, and struck its target at 446, impacting at 73 meters per second. 15 kilograms of explosives is typically insufficient to destroy a hardened industrial site. But this wasn't any factory, it was a semiconductor fabrication facility. The air filtration system for the clean room, capable of filtering 0.3 micrometers particles, instantly clogged with millions of fragments of metal and concrete. An electron beam lithography machine, worth $47 million, with 18 months of calibration, was destroyed. An ion implantation system, a military-grade processor storage bay, millions of dollars worth, were reduced to dust. Result, Russia's military chip production was crippled for at least 6 months. Within 6 hours, Russia had to reallocate strategic air defense assets to protect other remaining high-value facilities. This created gaps along the front lines, opening a window for HIMARS strikes and other Ukrainian attacks. As for cost, Ukraine spent $412,000 in drones and inflicted tens of millions in damage. But more importantly, they struck a psychological blow. If a drone could reach Penza, 630 kilometers from the border, then nowhere is truly safe.